I'm Dave Bly here at the Data Science Institute, and it's my pleasure today to introduce our colloquium speaker, Vikash Mansinghka. Vikash is one of the founders of the field of probabilistic programming. I'm going to let him eloquently tell you what that means, what it's about, but I want to tell you a little bit about its consequences and the characteristics of this field. So at a high level, probabilistic programming, as I said in my announcement, promises to let investigators easily explore the universe of probability models to solve their data science problems with customized techniques. Okay, so it gives you a language for expressing new ways of analyzing your data at the highest level. This is part of the reason why many people are interested in this. At a mid-level, for people like me who develop new machine learning algorithms, probabilistic programming gives us generic tools to think about algorithmic issues around inference and statistics and data science and machine learning, which is very important. At a low level, and perhaps most beautifully, probabilistic programming intimately connects deep ideas in probability theory, measure theoretic probability theory, with deep ideas in computer science around programming languages and computability. And so you can see it's really an incredible field. If we are sculptors of data science methods, then Vikash and his colleagues invented clay. One thing I want to mention, don't stress out about it, but he did this all when he was a graduate student in 2008, or in the years up to 2009, he got his PhD with Vikash Mansinghka. So this field has really become a bubbling revolution in machine learning, and Vikash, take it away.
Thanks, Dave. It's a delight to be here. Everything that I present today is done in collaboration with the members of my group, but I especially want to acknowledge Alexei Radl, Tejas Kulkarni, and Baxter Eves. So, my goal is to give a survey of probabilistic programming, and the bulk of the time will be spent on two probabilistic languages, BQL, which runs with a system called BayesDB, and Picture. BQL is a database language that's probabilistic. So it's designed to make it possible for users to query the implications of their data directly as SQL lets users query the data itself. Picture is a language for computer vision. These are quite different domains, but in each case, I'm going to be trying to emphasize how having the flexibility, the modeling flexibility that probabilistic programming provides enables either faster time to completion for certain applications or more interesting capabilities. Then I'll talk a little bit about general purpose probabilistic programming. So I'll describe our current project called Venture, which is attempting to build a general purpose probabilistic programming language that could in principle be used across all the application domains where probabilistic modeling and inference apply. And then I'll touch a little bit on the research roadmap, and especially some places where we're looking for. So before I get into any of the details, I just want to spend a few minutes giving a working definition of probabilistic programming to keep in the back of our minds for this talk. So the first thing that, in fact, it very, very closely is going to parallel what Dave said in his introduction. The first aspect of it is it includes a collection of languages and runtime systems whose aim is to simplify probabilistic modeling and inference for practitioners. And this is the emphasis. This has been the emphasis of many projects. Stan here, for example, which has been seen quite a bit of adoption in statistics, as well as some other languages. And it's the focus of a new research program in the Department of Defense. Now, another aspect of probabilistic programming is about pushing expressiveness. So trying to figure out what's possible if we're allowed to define our models and our queries over those models in terms of complex computations. And that's really what BayesDB and Picture are about, the two languages that I'm going to spend the most time on. But underneath all of that, there's the core technical hypothesis behind probabilistic programming, which is that we can represent probabilistic objects, the objects from measure theory and probability theory, as programs and languages. And Venture is fundamentally about that. So the view that this talk presents on languages and systems and new applications is one that's informed by a particular set of hypotheses about this level. So it's possible to do good probabilistic programming work up here. We're going to depend on interesting stuff from down here. Okay, so I'll start with BayesDB. So what do I mean by querying the probable implications of data? So here's a conceptual illustration first. Let's pretend that we had a database with some data about some patients. And it might include and we had variables like heart disease, weight, age, and missing values of various sorts, as is usually the case. Now SQL lets us filter and retrieve subsets of this data. So I could write a query, select heart disease, total cost of care, and age from patients where age is greater than 30. So find me those variables for some subset of the patients. And on this database, the SQL query is going to return rows 131 and 133. It's not going to know two of the values. And it's not going to be able to consider row 132 because age is missing. So it can't test the predicate. One entry point into BQL is to look at this query, which is closely related to select. Infer heart disease, total cost of care, and age from patients where age is greater than 30 with confidence 0.7. So you can think of this from a statistical perspective as a select with some kind of Bayesian imputation happening automatically behind the scenes. So the results you get back in this case include a filled-in value for total cost of care for patient 133. It includes row 132 because it was able to fill in the age with the required confidence. But this value here for heart disease for 131 is not filled in. Right, so it's not just going to fill in all the values you're interested in. There's a notion of uncertainty that's represented within the system, and you're allowed to query it based on the demands of your application. Another type of query we might be interested in is exploratory. We might say, well, what are the variables that probably predict height? So show me 10 variables, the 10 that you're most confident predict height on the basis of all the data that you have. And so you might get back a table like this with some variables. And then you might say, okay, well, I'm interested in studying the height and weight, the physiology of men under 10, but I don't have very many of them in the database. So can you concoct a synthetic population of men under 10 with 100 members that's informed by or reflects the statistical structure in the original database? And present that as a table so that I can do all the things I'm used to doing with databases and tables afterwards. Plot it, use it as the basis for further modeling, and so on. Okay, so this illustrates some of the basic statements in BQL, building off of SQL. What I'm going to talk about next is one application that I think shows some of BayesDB and BQL's strengths and weaknesses in the real world. So this is based on a database of satellites, Earth satellites, that was published and is maintained by the Union of Concerned Scientists. So you can see there's Earth, there's a lot of stuff in low Earth orbit, there's also this ring here for geosynchronous orbit with a reasonable number of satellites and then plenty that are scattered in between. And this database is available on the web. It's mirrored publicly on S3, comes to you as a text file. That's actually not too difficult to parse, but turns out to have serious quality issues, which we'll get back to in a minute. So when we analyzed this database with BayesDB, we didn't know very much about satellites. So I'm going to show you the queries that we ran to use this data and BayesDB to learn about that domain. So the first thing that we did is we said, show me a matrix of the pairwise probabilities of dependence. So this cell here, this matrix, has cells that correspond to pairs of variables in the original data set. And the darker blue it is, the higher probability that the two variables corresponding to the row and column are dependent. So this block of variables here has the perigee of the orbit, the apogee, the period, the orbit class, and its inclination in radians. So the kinematic properties of the orbit from orbital mechanics. And just as as a reminder, for an elliptical orbit, this is the perigee, this is the apogee, the distance to the farthest point. So these are deterministic nonlinear relationships, or I should say nearly deterministic nonlinear relationships, and that there are mechanical constraints at play. But several other groups of variables actually turn out to be identified as having a high probability of mutual dependence. So this block down here in the bottom right has the launch date of the satellite, the longitude, if it's in geosynchronous orbit, the contractor, the country of the operator, and the country of the contractor. So that's consistent with the fact that countries prefer to launch geostationary satellites that they can use, and that different contractors service different countries, and also that different countries got the ability to launch satellites in different decades in some cases. These other groups of variables reflect some constraints of satellite design and the ecology that actually launches satellites. Okay, so from my perspective, this is a way to get a kind of sanity check that the database coupled with the analysis that's inside BayesDB may give something sensible. It's also something that's easy for a domain expert to check. Now, the next query we ran was we said, let's find satellites that are unusual in terms of their expected lifetime. So show me the 10 satellites in increasing probability of expected lifetime. So that's going to be under a probability model that models all of the variables in the database, how probable is expected lifetime. So the least probable satellite is the International Space Station, which has an expected lifetime of 30 years, which is far and away higher than all the others. But the next two satellites are two military intelligence satellites that are, according to the database, in geosynchronous orbits, but with very, very short expected lifetimes. It turns out that both of these are data entry errors. If we dig into the notion of anomaly, we'll see that many of the anomalies in this database can only be found if you're doing a multivariate data analysis. So here I'm showing expected lifetime, and here the predictive probability of expected lifetime. Right? So what the value was and how likely BayesDB thought it was on the basis of all the data in the database. And this red line here is the cutoff for the top 10 least likely values. So up here, you can see the International Space Station. But many of the other satellites that are anomalous come from bands of expected lifetime anchored at a half a year or 15 years. And from the perspective of this variable on their own, these are entirely typical values. Right? So if you're looking for anomalies in the database, you need to consider relationships between the variables, which you might be aware of because of your domain knowledge, or if you had a comprehensive statistical model for the data. But you can't find these sorts of anomalies simply by doing statistics on single columns. I won't go into all of the anomalies that we found, but one group that I thought was particularly interesting are these 4 satellites, which are supposed to be in geosynchronous orbit around the planet Earth with orbital periods of 14 minutes, 20 minutes, and 2 hours, which is physically impossible. So this database has been in the public domain for maybe 5 to 10 years and has been mirrored in lots of different places. So from our perspective, these anomalies are interesting because, especially the multivariate ones, because they're actually quite difficult to find. Unless if you don't quality control each row of the database very carefully with domain expertise, you may miss a surprising number of these. So now let's take a look at what's underneath BayesDB, so how these inferences are being provided. So first, BayesDB is not based on a collection of machine learning techniques that are pieced together by some query planner. And the reason for that is that it's not clear that it would be possible to make a query planner that's smart enough. So this is a flowchart that's distributed with the scikit.learn machine learning library, a popular Python machine learning library, that tries to give a sense of how to solve various classic problems in computational statistics in terms that somebody who's, let's say, got a software engineering background or perhaps a domain science background can at least test unambiguously. And it involves paths that some paths succeed. There's kernel techniques that you can apply to classify data sets with fewer than 100,000 variables if they're labeled. But there are other paths, like this one, where if you have more than 50 samples, you're predicting a category, you don't know the number of categories, and you have more than 10,000 data points, it says tough luck, right? So the challenge in building something like BayesDB, the intellectual problem that we focused on, is how can we build a kind of probabilistic meta model integrated into a probabilistic programming language so that inference in that meta model implicitly solves the problems that this flowchart is trying to get users to solve on a per problem basis. So the basic workflow in BayesDB involves starting with some data. Maybe you have it as a text file. Then creating a BayesDB table or a Bayesian table. Then asking BayesDB to do some analysis. So you might say, initialize 10 models and analyze for an hour. Once you have the models, you can then query freely without reanalysis. So I might run infer, estimate, simulate in order as I dig into parts of data that are of interest for particular questions. Now, if I'm a domain expert or a statistician, then I might be only interested in this if I can customize the model. So I don't want to just rely on whatever generic model building facility is under the hood. So EQL is a probabilistic programming language that provides modeling commands that are just a bit more abstract than the typical modeling commands in Bayesian statistics. So you could say, set the type of some variable to be a count. And that's going to imply something about the probabilistic model that will be used to analyze it. Or ensure that B is independent of C, because you know that they're causally unrelated. Or try to model D with some regression of interest. So you can integrate background knowledge and domain knowledge when you have them, and add new data to the database, and the models will automatically update. So your queries don't have to change. The models can be updated transparently. OK, so yeah.
Can you break it by one thing depend on how
So the technical constraint is that the discriminative predictors have to be a feed-forward network, and all the inputs will be anything that you have not specified an explicit model for will be handled by the default non-parametric meta model, which I'll describe in a minute. So the inspiration here was the kinds of background knowledge that we've often heard, actually a bunch of them that I heard doing data analysis in industry. So there are a couple of challenges in implementing that workflow. The first is that for any given target variable, there's a very large number of possible predictors in any sizable database. So this is one dimension of complexity in building an automatic procedure. So maybe we would hope that there's some variable, some effect variable of interest that separates cleanly into two groups, which can be distinguished by some other variable, like x's and o's. But that's often not the case. The values we're interested in are mixed. And one explanation for that could be that this is just a marginal effect. Like if you're an x, you're slightly more likely to have a slightly higher effect than if you're an o. Or it could be that there are other variables that explain that. So maybe the x's that have a high effect, or at least a medium, mid-sized effect, and the x's that don't are distinguished by some other variable, which you could measure. So there's a very large space of possible explanations of this form, and that's only if you're trying to predict one variable. So somehow, whatever's inside BayesDB has to contend with this issue. The second issue it has to contend with is that even if you just have two variables, the dependencies can get arbitrarily complex. So first, they can range from deterministic to stochastic. Right? So, maybe this is a correlation of 1, correlation of -1, no correlation. All of these are certainly possible, but the situation's quite a bit worse. So here are 7 data sets this is from Wikipedia, that all have zero correlation. So there's a symmetry in each of these. That means the correlation between x and y is 0. So clearly there's predictive information in all of these. Because if you know x, you can infer something about y. But if you want to handle these dependencies, you need to be able to deal with nonlinear relationships that are quite stochastic. So the basic idea that we tried to apply in BayesDB is to build a model using an idiom from computer science, divide and conquer. Okay? So at a high level, the models that BayesDB builds maybe start with some data table. So here are the variables or the columns, and the rows are entries in the table. And what the models are going to do is partition this data into groups that can be modeled independently. And then model each group with some generic statistical model, like a mixture model. Okay? So how are we going to solve a high-dimensional density estimation problem? By turning it into several lower-dimensional ones. So let's just look at that in a little more detail. If I have a table with 4 rows and 3 columns, there's a broad range of different possible dependency structures that could be in that data. So in each of these pictures, a single color corresponds to all the cells in in the data matrix or the table that are modeled by that have the same parameters, the same primitive data model. So in principle, if I have this table, I could model each variable with a single simple parametric model. Or it could be that every entry in the table is actually idiosyncratic, comes from a totally different data generating process. The likely possibilities are the intermediate ones. So maybe for this one, here we're saying that D2 is independent of D1 and D3. So knowing about D1 doesn't tell us anything about D2, vice versa. But there is information that relates D1 and D3. So the structure that we use to model this data, so our goal is to model the joint distribution, in this case, of D1, D2, and D3. And so what I want to do here is just give you a sketch of what's mathematically going on in the types of models that BayesDB builds. So the first thing we need to do is describe this combinatorial structure using some vectors with discrete values. Okay? So this partition of the D's is going to be some vector, we're going to call it Z, and it's going to say that variable 1 is in group 0, variable 3 is in group, variable 2 is in group 1, and variable 3 is in group 0. So given that kind of structure, conditioned on that structure, we can look at the distribution of the variables. So here we're talking about the distribution of the variables given all the data. Here we're conditioning on this particular latent structure, this particular explanation for it. And under this structure, we're going to factor D1, D2, and D3 into the product of these two submodels. Then we can break these models down further. So the model for D1 and D3 is going to break down into a mixture. So of the purple model versus the brown model, roughly speaking. And then each of those we're going to divide. So the joint distribution for D1 and D3, just zooming in on the purple section, is actually going to be a product of independent models for D1 and D3. And then finally, those basic models are going to have be subject to some standard conjugate Bayesian analysis, let's say. So we need to model the entire table. We have to reduce that to elementary Bayesian statistics problems. And we're going to do that by somehow positing a latent structure that divides the data into the independent blocks that can be modeled separately. So fortunately, there's technology to do this. It turns out to be a pretty direct application of tools from nonparametric Bayes. So here, what I'm describing is the generative process for the meta model that we use to infer the models that I was describing previously. So the details of this aren't all that important. One thing that it's worth noting, though, is that this kind of notation for a model like this, which has to place probability mass on all possible structures of the sort that I was showing you before, you can read as a kind of program. So for example, this line is saying there's some parameter alpha d, and you can generate it by drawing it from a gamma distribution. Okay, so that's how you can read these instructions. And the crucial ones are this thing which generates elements of Z, that vector I was showing earlier that partition the columns. Something that generates a partition of the rows. And then something which actually fills in the values from each cell from probability models based on the type of data. So that's the important structure in this meta model. There's a large number of possible structures. So if we take this problem seriously, maybe from one perspective, we might possibly have simplified the problem by turning high-dimensional data modeling into low-dimensional data modeling. But we have another problem, which is that there's a very large number of possible structures which describe how to do such a division. So for a 4x3 table, there are about 4,000 possible structures. So that's different valid settings of the Z and the Y vectors I was showing earlier. And the approach we use to solving this problem is actually Markov chain Monte Carlo. So what we're going to try to do is explore the joint distribution of all of those latent variables in the model and the data. And what I'm showing on the top here, just to give some intuition, is what the algorithm for inference looks like. So I'm showing the data matrix. Here it's partitioned into 3 groups of variables that are being modeled independently. And the red is shuffling rows in each of these views between categories or clusters, and then shuffling variables in between views. So just stochastically exploring the space of dependencies in this table. And it turns out that with those relatively simple computational kernels, you can end up with a valid MCMC scheme for exploring the full joint density under this model I was showing earlier. So this funny thing here is essentially a kind of objective function, if you like, that you can use to understand how good a partitioning you found. And intuitively, good partitionings will look less noisy in this kind of view, because they'll be modeling data together that's actually well explained. It'll be finding a coherent explanation. So to give a sense of the robustness of this, it's helpful to take a look at what happens when we feed it the zero correlation examples I described earlier. So these are the outputs of simulate. We said simulate about 10,000 times after having analyzed a table that had each of these data sets in turn. And this already, I think, gives one way to get a sense of some strengths and limitations of BQL and BayesDB. The qualitative structure of these nonlinear stochastic relationships is pretty faithfully captured. But it's captured in crazy ways in some cases, by putting down lots of clusters. So one consequence of that is the memory cost for certain kinds of data sets can be surprisingly high. The asymptotics are quite favorable, but in practice, maybe it's hundreds of megabytes for a data set that's some very, very complex, purely deterministic function. But when we've moved away from the setting of adversarially chosen data sets and looked at data in the wild, we found that given how limited a view of the world our data sets typically give us, often there's enough entropy that this kind of a description is actually not so bad. Now, BayesDB is also applying divide and conquer at a higher level. So earlier, I talked about how it's implementing a modeling strategy based on divide and conquer. But BayesDB also separates the process of modeling from analysis in a way that I think is interesting as an alternative to standard workflows, essentially, for statistical inference. So maybe in multivariate statistics, we often think of a data generating process, which is somehow implicitly behind a population. You may not know very much about this at all. From that population, we obtain a sampled subpopulation. And given that sample, we may be interested in properties of an individual or a new individual that could be added to the sample. So one way we can answer questions about this data is by constructing estimators, F, for various properties we're interested in. So we can just come up with good, robust, fast, hopefully somewhat transparent algorithms that directly answer individual questions, that take the data as input and spit back some kind of answer as an output. And many of us are used to using these. Maybe a simple example is just, is there a non-zero correlation between two variables? It's a test for that under certain assumptions. But a difficulty that this perspective exhibits is that for each question, in general, you need a different estimator. And that means you need to know how to choose good ones, choose the right ones, diagnose unfortunate choices or inaccurate choices, and in some cases know how to design new ones with an off-the-shelf tool that's available. So I think BayesDB is inviting a different lens on this category of questions, where from the samples, we're going to build general purpose models, where by general purpose models, let's say all their latent variables are going to be represented by CC here. Given that information, I have a complete model of all the variables in my multivariate data set. So to work with a model class where, given the right setting of its latent variables, it can emulate any data generator or a sufficiently broad class of data generators. So then, the problem of modeling is about going from data to some estimated models. But now, reasoning about new individuals can just boil down to Bayesian inference, integrating out what the data generator, the underlying data generator, actually is. And depending on the structure that the underlying model family exposes, a wide range of questions can potentially be answered. So for the one that I showed earlier, questions about dependence, independence, mutual information, similarity. So these sort of standard quantities that people construct estimators for, but which can be tricky to apply in some common situations. All of them can also be directly estimated as model-based inferences just under the model that's inferred for the data generating process. That's right. That's right. And this is in particular, so this posterior predictive distribution is integrating out or summing out full joint distributions. Sort of the important way to think about it. So it's kind of related in a way to BayesNet structure learning. You could sort of imagine if you could learn a good BayesNet for any table, given missing values and data types and all those considerations, then in principle you could try to do this with BayesNets as well. Right, which would be integrating over BayesNet structures and parameters. The ideas from computer science, I think, like divide and conquer, helped lead us to a model family which was easier to scale than BayesNet structure learning. Okay, so let me give one other quick example. So this one is actually an example from an analysis that we did at a startup company that I had, which worked with an ancestor to BayesDB. So the data set is the Dartmouth Atlas of healthcare, which has about 4,000 hospitals and a bunch of different variables, including 4 quality scores. So one query that's natural to run on this data is to say, show me the columns, order them by how probably they're dependent on or with the quality score variable. So QualScore is a survey instrument that was applied to all the hospitals. So if you do that and you plot the results, you get something like this. So on the y-axis is the probability of dependence, 1 minus the probability of independence. And here are all the variables. So these first 4 variables all turn out to be quality scores for different aspects of the hospitals. So there's overall quality, quality for 2 kinds of heart disease, and quality for pneumonia, essentially. And then all the other variables are, with high probability on the basis of this analysis, independent. So that doesn't just mean there's no correlation. That means that it's likely that there isn't a pattern of any of the sorts of patterns I was showing earlier, these nonlinear stochastic dependencies. So we thought this was interesting because these kinds of negative conclusions are relevant often for decision makers, especially in policy, but they're hard to produce by statistical analysis. They're labor intensive. And I'm certainly not suggesting that in general people just trust some black box Bayesian database. But I do think that we're more likely to be led, for example, to the right model-based tests to do on a custom basis if we can give domain experts who understand the domain and the variables the ability to rapidly converge on hypotheses that are in some sense statistically robust or reliable. then if there's an expensive or risky decision to make, more custom analysis can be done. So it's interesting to note that in this case, this conclusion that patients in higher spending regions, for example, received 60% more care than elsewhere but did no better than the other patients, was the centerpiece of a New Yorker article by a doctor who was involved in the formulation of the Affordable Care Act after this article. It's also interesting to look for anomalous hospitals. So here I'm showing a scatter plot that's much like the expected lifetime plot I showed earlier. The interesting thing to note, this top hospital here, McAllen, Texas, turns out to be anomalous on many measures and also is frequently written about in the popular press on this issue, used as an example to illustrate some of the absurdities of the current state of affairs. So, okay, now we've gotten a sense of one domain-specific probabilistic language. And I focused on this one because I think it reflects a strength of probabilistic programming that's not about modeling exactly, but rather about enabling end users to ask and answer the questions that they're most interested in. So the language is for them in this case, as opposed to for probabilistic modeling experts or researchers, primarily. Now let's take a quick look at a language for a totally different problem. So this language is called Picture, and the problem we're going to look at is computer vision. That's the domain. Where what Picture does is it tries to implement a proposal for computer vision, which is sometimes referred to as the inverse graphics proposal. So computer vision, you can think of as the problem of going from images to scene interpretations. So maybe geometric descriptions of objects, the presence or absence of categories, like this scene has, you know, a ball, a cylinder, and so on. And one way to think about this problem is in terms of computer graphics. So computer graphics gives us executable models that go from scenes to images. So it's appealing to think about vision as the process of a Bayesian inversion of that kind of model. In fact, this idea goes back to Helmholtz, back before graphics was formulated, and it was thought of as inverse optics, that maybe our visual system can solve problems that are in some sense like this. But of course, this idea is not how most vision systems are engineered. Instead, the field has seen enormous success for quite a different architecture, which is based on bottom-up processing using feed-forward pipelines that are each based on statistical models, which move from input pixels to various kinds of feature spaces that represent increasingly abstract structure in the input images. Now, there have been some approaches to inverse graphics made in computer vision. So some excellent work trying to use complex search techniques to explore the space of scenes, some work that's trying to use neural network learning to directly invert graphics engines. But it's proved pretty difficult to scale this kind of approach up, at least so far. So with probabilistic programming, we're going to try to take inverse graphics so seriously that we take it literally. So we're going to build probabilistic models out of scene generators, which generate scenes that are fed into renderers, and use stochastic comparators to compare the rendered images to the data to get some sort of compatibility score. So this is like a kind of approximate Bayesian computation over the space of scenes. Not exactly that, but it's like that family of techniques. And we're going to represent each of these parts of our model with probabilistic code. So this is quite important because we can't write down an analytical formula that defines the density of an image under some renderer. In fact, we often can't even evaluate the probability of a scene under some complex generative process, but we can write the code for it. So this structure induces a probability model, which we can then apply Bayes' rule to and try to invert it. And part of this proposal is to try to do this inversion, to do inference using only general purpose techniques. So for this to really feel like inverse graphics, we need to be able to change the scenes without having to change the inference algorithm. So that's the kind of modularity that we're looking for. So a few years ago, we had an implementation of probabilistic graphics programming in our language venture. Here's one of the applications, which is inferring a 3D model of a roadway. It's actually from single images. which we thought was interesting, but was also clearly limited from a computer vision perspective. The space of possible road scenes is actually fairly low dimensional. So since then, we've been working on a language called Picture, which attempts to scale up the basic proposal. And I'm not going to go into the technical details of Picture, but there are just a couple of key ideas that I think are interesting, and they're actually quite surprising to me. So the basic approach for scaling up inverse graphics was to integrate deep learning into our probabilistic programming system. So implement a stochastic comparator that uses the features from a neural network to compare the rendering to the real-world image. But we also had to integrate ideas from programming languages. So we have more complex sampling strategies, elliptical slice sampling, Hamiltonian Monte Carlo, and bottom-up proposals that are all constructed by a compiler that takes the scene generator and actually trains bottom-up models for doing inference by running the scene generator forward and then using the neural network to get features to make proposals in reverse. So here's an example where we're going to take a single image and try to infer a 3D model of the human pose from it. So on the right is the initial guessed scene. The scene generator here is an off-the-shelf rendering library. So initially, the pose changes quite a bit, but over time, actually the structure stabilizes and it starts to make finer-grained adjustments. And just look at those dynamics again. The initial switching is due to the compiled bottom-up proposals. And afterwards, the kind of gradient-based search takes over. Another application we looked at was 3D modeling of faces. So here, input faces. Some frontal view, some profile. And here are reconstructions of those faces using 3D models inferred by a picture program. And here we're showing reconstructions from a commercial baseline vision system, which are in general quite good, but one fundamental difference is that in Picture, because the hypothesis space is really the space of scenes, it's easy for us to include an unknown rotation. And as modelers, we're not responsible for designing the inference algorithm to handle that rotation. It's the compiler's job. So as a side consequence of being able to reconstruct frontal faces, we get the ability to reconstruct profile faces. Whereas that's quite difficult for manually engineered or learned bottom-up vision pipelines. OK. So both of those applications and a couple of others, there's actually a paper online that you guys can read about this, fit within this template picture program. And the only things that needed to change were the scene generators. So we didn't change the code that automatically generated the inference strategy. And to get a flavor for what that looks like, on the left here is a real face. A face from the data set, and here is the process of inference applied to that face. I'll show it again. So it's a hypothesis space with quite a different structure than the pose one that was shown earlier. OK. So taking a step back, I've tried to give a couple of examples now of domain-specific probabilistic languages that are really motivated by classes of problems that have been historically approached with modeling and inference. But because we can express models using programs, and we have support from our programming system to generate inference strategies that would be difficult or, in some cases, nearly impossible for us to build by hand, we're able to work with rich, expressive models that can do some interesting things. So now I'm just going to say a little bit about a general-purpose programming model implemented in a system called Venture, which is designed to be able to handle problems from domains like robotics and statistics, but also, at least in principle, to implement probabilistic languages like BayesDB, like BQL and Picture. The basic difference between Venture and other probabilistic programming languages can be thought of as follows. So many approaches to processing ambiguous information end up with some estimation algorithm that's then implemented and then compiled into some executable that's hopefully fast. Now, some subset of these, maybe you would think of random forests and a MATLAB implementation. Some subset of these estimators can be derived by applying an inference strategy to some model. So we'll call these model-based. And maybe an example would be classification by logistic regression. And the estimation algorithm will be make a simple Monte Carlo estimate of the posterior mean, and then we'll use Hamiltonian Monte Carlo to generate those samples. So many probabilistic programming languages and systems have focused on model-based estimators, where they give a way to represent generative processes or density functions using code and generate executables by some compiler or runtime system. This is appealing and is one really important approach. It does run into a difficulty, which is that approaches that don't involve models are out of scope. But another challenge is bridging the gap between the model and the executable. The picture up here suggests that there's knowledge that human experts apply about how to do inference and how to construct estimators that ought to intermediate. In Venture, there's still a model given as a program, and I'll give a couple examples in a minute. There's executable code, but there's also a program in the same language that represents the inference and estimation strategy and may not even have a model at all. So you start with a program that just describes your model. I'll say in a minute how you get to the inference and estimation strategy, but given this, getting an executable is just a traditional compiler problem, because this is code that formalizes the estimation algorithm from up here. Really, it's sort of fusion with the inference strategy. Going from a model to an inference strategy is not really a compiler problem. It's either something that a human programmer can learn how to do, an inference programmer, which is one of the roles or hats that machine learning people, I think, implicitly wear. It also may be appropriate to address with a kind of planner or a decision theoretic system that can make uncertain decisions, and will make decisions under uncertainty about the relative performance of inference strategies. It's also, I think, interesting from a foundational perspective to consider useful program transformations that stay within this formalism. So how can you optimize inference algorithms on their own terms before then compiling them to optimized machine code? So let me give a concrete example of Venture. So here's a program fragment that defines a model for inferring whether or not some numbers come from a standard Gaussian with zero mean unit variance, or from some biased Gaussian. Okay? So this top line says, is there an offset? Well, flip a coin to decide that. This next line generates the mean. So what is the offset from some uniform distribution? Now the mean we're going to use for our Gaussian depends on whether or not there's an offset. If there is an offset, then its mean is whatever we generated up here, otherwise it's 0. And there's this procedure called trial, which then generates Gaussian draws whose mean is given by this mean variable up here. So you can read that as normal code in a JavaScript-like syntax that produces values randomly. And if we were to stop the Venture interpreter at this execution point, we're just typing it in, what we might see is that the distribution that we'd get from repeatedly trying to sample the mean will have a spike at 0, because it probably doesn't have it, in this model, there's probably no offset. But there's some probability the mean is all over the place. Now we can add some data. So you do that by saying, say, observe that one invocation of the trial yielded 8. So let's say we see a data set, an unusual data set under the model where 8 was observed 4 times. So there's probably an offset. It's probably not a standard Gaussian. It's probably biased near 8. We can do inference. Here we're using the what we call the Bayes inference strategy. It's rejection sampling. So essentially guess and check. And that yields a new distribution on the value of the sampled mean, which is concentrated to the right, shifted to the right near 8. So we have the model, which has this broader prior. And then we see some data, and the posterior is shifted. Now, here's a different program for solving the same problem that has the same model, so that's unchanged, but has a different inference algorithm. So this is going to do a kind of MCMC. So after seeing 3 data points here, we're going to run a Metropolis Hastings algorithm that's denoted by this MH here that chooses random variables at random and resimulates them from the prior. And that induces a distribution which is shifted, but not all the way to the right answer from rejection sampling. Then maybe we see another data point, and we do some more inference, and we end up with a distribution at C that converges to the same answer rejection sampling gave. So the distribution shifted to the right, to A. But what if we want to do a non-Bayesian kind of inference? What if we wanted to do optimization, let's say? So one thing we could do is use gradients to evolve our estimate of the mean to maybe make quicker steps towards highly probable values than the generic algorithms I was showing earlier. So Venture allows this through a linguistic construct called @tags, which basically dynamically broadcasts, you sort of think almost like Twitter hashtags in some sense. They dynamically broadcast names for random variables that you can refer to later. So you might say that whether or not there's an offset is a discrete variable. What the offset is continuous. And the inference strategy is going to do one thing, Metropolis Hastings for discrete variables, and this Nesterov accelerated gradients thing for continuous variables. So this is just meant to give a flavor for how you can compositionally construct inference strategies from reusable pieces, staying within the formalism of a single probabilistic programming language. Yes?
So is what you ran there optimization technique or inference?
Well, so here I'm going to use inference inclusively. Really, this is, I think, in the midpoint between something that one person could look at and call approximate Bayesian reasoning, and another person could say is some kind of stochastic search.
So it's like little math estimates inside of it.
That's right, inside of it. In fact, I would say that many stochastic searches that have gradients and randomized moves implemented, or I would say many Metropolis Hastings algorithms that are built out of these pieces might be as well explained as stochastic search procedures as they would by, as programs that are really sampling from the true posterior. So this is just meant to give a flavor for what it looks like to write code in this funny, both declarative and procedural way, where here I just write an incomplete program that has variables whose values I don't know. Here I supply constraints. And here I give hints about how those two should be reconciled. And crucially, as distinct from other declarative programming formalisms, everything here is executable. So this is not like a theorem prover, let's say, or in some sense it feels quite different than logic programming. You are explicitly controlling the algorithm that the machine uses. But it may be that up to the level of detail you care about, you can kind of ignore what's here and just use something generic. And entrust it to a later optimization phase to come up with exactly the right inference algorithm. Okay, so I just want to wrap up with some demos. Here's an example problem from the DARPA program. So each year over the next several years, they're giving us a new set of challenge problems from different domains. So one of the problems they gave us for Venture was simultaneous mapping and localization. So we have data from a LiDAR, a laser range scanner, which basically measures the distance to obstacles. And we want to build a map of the environment around the truck from that data. I'm not going to show the model for SLAM. It turns out the model for that is maybe 15 or 20 lines. But I want to highlight that you can change which algorithm you use by just altering a few lines. So this top line actually turns out to be sufficient for particle filtering. This next line is sufficient for a hybrid sequential Monte Carlo MCMC scheme. And at the bottom, there's an inference line added to make the obstacles an objective inference. So maybe previously they were assumed to be known, and you can add this line and now make them an objective inference if you were willing to put some uncertainty over them in the original model. Okay, so the demo I want to show you is another type of application that you can build with a general purpose probabilistic programming system. So here I'm showing curves that are generated from the prior encoded in this program. You can see there's polynomials of varying degrees, sine waves, linear combinations of the two. And as I start clicking, we're going to see the distribution on executions shift. It actually doesn't take very many samples for this thing to converge to reasonable confidence that the data was generated by a linear function with some noise. So the red circles around the data points are the inferred level of certainty in the model, which is a random variable. And you'll see every so often the thing will get a little bit wigglier, and that's when it's exploring a part of the posterior distribution where it trusts the data less. And under that assumption, maybe the curve could be drawn from a larger range of possibilities than just a line. And the reason I think this is interesting is because with probabilistic programming, it becomes easy to integrate modeling assumptions that correct for biases in standard statistics. So for example, if I click there and add a data point, we see here it's turned gray, and it didn't shift the slope. I'll show it again. So I click here, and it's gray. Right, you see the slope kind of shifts up. Ah, yeah, so great. Now we'll see another, right. So in this execution for a while, it turned red, and then the curve skewed, and then snapped back. So this probabilistic program has a random variable for every data point, which is trying to decide, is it an outlier or not? OK, so let me wrap up with the research roadmap and summary. So there are a bunch of directions for probabilistic domain-specific languages. For BayesDB, the ones that I want to highlight here are integrating record linkage and natural language processing. So what if we allowed stochastic foreign key and primary key relationships and did inference over them? So maybe we could have not just denoising of the values, but deduplication simultaneously using the inferred probabilistic model. And for picture, one of the things we're working on is using procedural graphics. So the idea where code is used in graphics to generate scenes to make richer models for possible shapes. So making statistical or stochastic procedural graphics models. It would also be really fun to try to make something which connects a picture hypothesis space to an iPhone and a 3D printer. Because then maybe you could take a picture of something and get a 3D model and then send it to a 3D printer to produce. And for general purpose probabilistic programming, there are a bunch of fundamental directions. But the most important ones I think, are addressing the computational complexity questions. So what probabilistic programs are tractable? And understanding how this kind of representation can help us reintegrate areas in AI and other decision science, like economics and psychology, that are all about various kinds of approximate decision making under uncertainty, or have that as a central component. And the most speculative part of the roadmap is to consider this as a proposal, not just for programming, but also for machine architecture. So we've only done a little bit of work on this so far, but I think it's interesting to consider what would happen if we had a stack for computation that builds on stochastic digital gates and stochastic finite state machines, and uses that as a hardware substrate for implementing probabilistic programming. And maybe we could make probabilistic reasoning a bit more ubiquitous. So, in summary, I think this wasn't the case 2 years ago, but now I could say that I think there are expressive domain-specific languages that solve useful problems based on ideas from probabilistic programming. And here are two examples. Stan is another excellent one. And I think there's a path to general purpose coverage. So one could ask, what would the Fortran or Lisp or C of probabilistic programming be? Right? If BayesDB is trying to be the sequel, or Picture is trying to be inspired by OpenGL. And one key idea, we don't know, but we think one key idea is going to be to make inference programmable. Thank you very much. Any questions? Yep.
You made this offhand remark that you're not telling people to believe this result, but it sure looks like you are. On the validity of SQL queries and asking people to believe it, but it also looks like, so have you thought about how to check this model that you are?
So that's a fantastic question. I mean, let me just elevate it a little bit. You know, we worked on BayesDB largely because we're interested in improving the quality of empirical reasoning as well as the access to quality empirical reasoning. So there's two aspects to my current answer, but I'd say this is an area we're still working on pretty actively. The first is, how do we convince ourselves that this is a reasonable thing to do? Or how would a BayesDB developer or expert gain confidence in the meta model and any particular schema or adjustments to an individual model? And there's a number of model checking techniques that are quite natural to apply here. The most basic is some support for posterior predictive checks.
You have it, right? If you can,
that's right.
You can impute the data that you don't see, you can impute the data that you do see.
Exactly, that's right. That's right. That's exactly right. So we use that as an internal diagnostic. But I don't have enough experience with models for general heterogeneously typed data tables to understand how to, for example, scale all the different probability models of different types so that aggregates are interpretable to an end user, you know, who won't know that a number, a binary choice, all these other data are sort of, you know, what's a good or bad answer, right? So one reference set that gets to something we can't show end users is, you know, here's how well naive Bayes does predictively. Here's how well a mixture model does predictively. Here's how well the default meta model does. Here's how well your customized model does. Okay, maybe you should back off. Okay.
Have you explored that, the predictive performance out of sample on your
Yeah, that's right, absolutely. I'm happy to talk about that in detail offline, but the short version is we appear to be seeing the right invariance, which is that it does better than the hypotheses that are nested within it, and it's competitive with many other discriminative techniques, but typically not better in accuracy. There's another element, though, which I think is just as important. So how would a naive user, by naive I mean statistically naive, gain confidence in any data analysis technique? So I had an interesting time at the startup talking to consumers of data analysis about this question. And they would say things like, well, you know, I have an analyst who has given me a model, and I think they're really smart. And I've had analysts say, I came up with a bunch of regression coefficients that sat on the shelf for 6 months because I couldn't convince the boss that they meant anything. So I think that's a crucial validation problem. And I definitely don't have an answer to that, but I think one interesting step would be to make it possible for people to interrogate models without knowing statistics. So that's, I think, an interesting use of simulate. Right? I stick in a database, and I'm a doctor, and I know something about the blood pressure of kids because I learned it in medical school. And I look at the predictions. So do posterior predictive checks against the common sense model that people have in their heads. But that's a very important area and one that I'd love to hear thoughts on. Yes. Oh.
So you showed us different ways to do inference, or maybe there's also a default way of doing inference, but is there also a way to say, okay, I give you 30 minutes, can you find the best inference method?
That's a fantastic question. So I was going to say something about that, but here's what I'll say. So at the heart of Venture, like VentureScript is a user-facing language, which was designed for interactive modeling and inference, or alternatively as a kind of formulation of discourse, right? You know, proposition, observation, inference. Okay. But what you're talking about is a kind of meta-inference, maybe, right? So underneath what I showed you is a language that's designed for that, in which VentureScript is one application. So I think it's a fantastic idea. I think it's necessary. One of the reasons I think it's necessary is because I'm so bad at predicting which inference algorithms are going to be any good. And I don't think I'm alone in that difficulty. So I think we need some decision theoretic support. But it's also clear that I have theories about how to do it, and I'm sure you do too, right? So let's say you're watching a sampler. You can kind of go, oh, now it's stuck in a local minimum. I better restart it. It's never going to get out of there. And you might be wrong some of the time, but it's useful to make decisions under that model, right? So we had a student who tried to build an HMM model of the energy function in MetaVenture of some inference program running on some other model in MetaVenture, and then do the decision theory using inference in MetaVenture to try to decide whether you should keep going with the inference program or restart from the prior. It's quite inconclusive at this point, but I think it's a fantastic and important area. And in fact, for PL people, if they're programming languages people here, there's something interesting that came out of the DARPA program. So there were reflective languages that were attempted in the programming languages community. I mean, some of them were quite beautiful, but they ran into many challenges, which was, roughly speaking, that people had difficulty programming these reflective programs, because now your normal programming problems started to have elements of compiler design. So I wonder if probabilistic modeling can help here. So it's a great question.
This is kind of piggybacking on something that was mentioned earlier. There's still a way of thinking about it that I'm totally clear on. So in some of these cases, there's kind of like an appeal to this gives like a reasonable answer as the output for the cases or for the factor thing. But I don't really have a clear sense of whether it's doing a point optimum kind of solution, or if it's giving me a posterior. And it seems like it's not totally clear which of those is doing in some of these cases. Is there a way you can kind of clarify?
Yeah, fantastic question. So the question is, is there posterior inference happening here, or is it optimization, especially in the vision example? So I got there. Okay, so you can do either or both optimization and sampling. So it's possible to express all those combinations. Now, as to which one we're actually doing, in some sense, that's an empirical question for some inference programs.
Yeah, so like if it's a bad probabilistic optimization, it'll give you like an optimal, but it won't give you a good posterior.
Yeah, I mean, this.
You have like a sense of.
Yeah, that's right. That's right. So, well, it's interesting. So for the road scene problem, actually in our paper, I don't think I have this. Yeah, I removed it from the backup slides. All right, well, in the road scene problem, we are getting good posteriors. So, one of the ways to check it is model criticism. So you showed a frame that violates the assumption that there's one road, like there's a road crossing, and you see this broad posterior with the modes that you would expect. Okay. Now, for the human poses, it's tricky because we're having a hard time coming up with stimuli that are actually supposed to be multimodal. Now, my student is also collaborating with some people in cognitive science who do psychophysics of vision. So you can try to see if there's posterior uncertainty on artificial stimuli and how that relates to our perceived uncertainty, like when you have the Necker cube that switches, or those sorts of rivalrous percepts. But I think it's some senior vision people will say that they're very confident that the energy landscape over scenes is unimodal when you have the right model. And maybe there's an evolutionary argument like that supports that. I'm actually not so sure, but that's something that's a really important issue.